Started recording. Alrighty. So for integration by parts, it basically says that if you have two functions that are basically having continuous derivatives, we say the following. We say u times dv, the integral of this, is equal to u times v minus the integral of v du. So as I go through this particular video, I'm going to go by do it by a series of problems, maybe like about 4 or 5, and I'll try to give you like some tips as I go along the way. So let's start off with an example. Let's say if I have, I don't know. So this was an example I was working on earlier with one of the students. Let's say if I have the integral of just x squared e to the x dx. Essentially, what you want to do is, whenever you're going to tackle integration by parts, your u, right? You choose your u in such a way where you know that finding its derivatives is easy, right? In this example, e to the x derivative is easy, right? It's simple because the derivative of e to the x is e to the x, but that won't be the case here. Our u will be x squared, right? The reason why our u is going to be x squared is think about all of its derivatives, right? Take the derivative of x squared. What is it? 2x. Take the derivative of 2x. What is that? 2. What's the derivative of 2? 0. So because you end up to get the derivative of x squared, repeatedly taking derivatives to get to 0, then you know that your integration by parts is basically finished, right? So first you say let u be equal to x squared, and let your dv be e to the x. Okay, so what I need to do with u is get its derivative, right? So what is the derivative again of 2x, of x squared? We said it was 2x. I'll just write it out. And the antiderivative now of e to the x is just e to the x. Okay, so by the integration by parts, what you're essentially going to be doing here is taking u times v minus the integral of v times du, right? So we're going to have here, this one? That's my v, so that way I can distinguish. Oh, but I should mention that. So usually when I write my v's, I put like a little mark on it to distinguish between a v versus a u. Yeah, and sometimes my u, if I don't write it in this particular manner, it can look like a v. Yeah, so my bad. So I put. Oh yeah, it looks like a square root for real. Can you explain why you found the antiderivative of v? Yeah, sure. So essentially what you want to do is you try to let dv be the more complicated portion of the integrand, whereas u is the more simpler part. But the thing is that, yes, I agree with you as you said earlier, the derivative of e to the x is easy. But if I put something a little bit more complicated now, let's say e to the power of x squared, e to the power of x squared, then every time you would have to take its derivative, you would have to use a u sub, right? So I'm trying to avoid the u sub there, essentially. So anytime you have sort of like a polynomial, such as x squared, a monomial term, a single term, if you continue to take its derivative will get to 0, which means that my repetitiveness of the integration by parts will be finished. Okay. So again, just applying the formula, I do u times v, so x squared. Hold on, let me just write out this line. Times e to the x minus the integral of v, which is e to the x, times du, which should have technically said 2x dx. What's your question?
How do you know which one to use for like u and v?
I just said it. If e is raised to any other power than x, then it sort of becomes complicated because you would have to use a u sub.
Talk about it in general.
Well, I will. Let me finish the example first. How about that? And then I'll show you like my tips. I'll show you my tips, okay? I'll show you my tips. I just want to let this be like our icebreaker, all right? I'll give you the tips out. All right, so that line that I wrote there with the arrow, inside of the integrand, your integrand, you could have rewrote it as 2x times e to the x dx. And what that would imply is that you would have to integrate by parts once again. So you have to make another u and v selection. So you just keep it simple. You say your u is x, now 2x, and your dv is e to the x. Right? Now, technically speaking, I should have said dv was e to the x dx, right? Technically speaking. So I'm just going to correct my formality. So here we have, again, let u be 2x, dv be e to the x dx. Now, if I take the derivative of 2x, that's just 2 du, and our v is going to be e to the x. Okay, so apply integration by parts again. Just remember a couple of things. When you apply integration by parts multiple times, everything that came beforehand, you've got to keep bringing it down. So I have to keep bringing down this x squared e to the x, and of course that minus sign, right? So it's x squared e to the x minus, I put a big bracket here. The big bracket is going to indicate that I am doing this part, 2x e to the x by parts, right? The integral by parts, integration by parts. So we have 2x e to the x minus the integral of, or I should have said 2x there, of v times du. So it's, I can put the 2 in front. We have 2 e to the x dx. Now, I can do integration by parts again, but I don't necessarily have to. Here's why. If you look at this term, 2 e to the x, that's a constant multiple times your function e to the x. So you can pull the constant multiple out. And we already established that the antiderivative of e to the x is just itself, right? So in my next line, I will say we have x squared e to the x minus 2x e to the x. Now, again, I'm just distributing this negative sign here. So when I pull the 2 out, originally it would have said negative 2, but because of the negative that was outside of the bracket, the negative 2 becomes positive. So it becomes positive 2, and then the antiderivative of e to the x, which is itself, plus c. All right, just remember this was an indefinite integral, so therefore I need to have the plus c at the end. And that would be my solution. Okay? Yes, I did. What I did was inside of the bracket, when I went from the second to last line to the last line, I distribute the negative sign inside of the bracket. So 2x e to the x becomes negative, and the negative 2, right, where I said pulling this 2 out, the negative 2 now becomes actually positive. If I leave this integral? No, I integrate it. Oh, okay. Because when I pull this 2 out, it's just the integral of e to the x dx, which you can integrate without integration by parts. Okay. So there's a little tip, by the way. I'll give you tip number 1, and I'll write it on the screen. So if you have integrals in this form, let's say x to the n times e to the power of ax dx, or I have the integral x to the n times sine of ax dx, or the integral x to the n cosine of a to the x dx. Your choices here for these common integrals is let the monomial term, single term, x to the n be your u, right? So essentially, in these examples here, u is always going to be x to the n, whereas the dv, the complicated part, will be essentially e, sine, or cosine, depending on what you have. Okay, so I want to make a second video In the second video, I will show you examples now of these